Hello and welcome back to this series on storing things in memory. We've already looked at length at how we can store binary numbers in memory, and last week we looked at how we can store characters in memory. Today we're going to look at how we can store negative numbers in memory. As we've looked at storing numbers in memory using the binary system, the assumption has always been that the numbers are positive. We haven't yet seen a way of storing negative numbers in memory, which is obviously a requirement of a complete computational system, and today we're going to take a look at a couple of approaches and indeed the actual approach taken by computers for storing negative numbers using binary. The way that we store negative numbers in decimal is to write a dash, a minus in front of a number to signify that the number is negative, and we could take a similar approach when thinking about storing negative binary numbers. Perhaps we could have some sign in front of the number to notify us that the number is positive or negative. For example, this is a byte. We could use the leftmost bit as a sign. We could use 0 to represent a plus or a positive number, and the 1 to represent a minus, a negative number. But mathematically, this approach is not ideal. We're going to use 4-bit numbers here just to make the maths a little more simple. 5 plus minus 6. Here we're representing the 5 positive with the 0 as the leftmost bit, and negative 6 with a 1 as the leftmost bit. The rest of the number representing the absolute number itself. Now, doing the addition the same as we would in decimal, going from right to left. In the first column, 1 plus 0 is 1, and in the second column, 0 plus 1 is also 1. In the next column, 1 plus 1 is 2, so we take a 0 and roll the 1 over. If we carry the 1 onto the flag column, 1 plus 1 is 0, and we ignore the carry because we're working only in 4 bits here. That gives us the number positive 3, which, given that we started with 5 plus minus 6 and we were expecting minus 1, is obviously incorrect. And if we were to take a look at a number of other cases, we would see quite quickly that simply addition with negative and positive numbers does not work using this simple primitive flag system. The impact of not being able to add numbers directly is larger than you might think. What it means is that we're going to have to manipulate individual bits before we can perform additions. And CPUs don't like to work with bits, they're actually built to work with bytes or larger. So these operations become increasingly expensive. The problem is magnified when you realise that a lot of machine instructions inside a CPU require addition functions. If we're now adding some extra complexity before we can add any numbers, we have to check whether it's a negative or positive and manipulate the bits accordingly. You're creating a lot of complexity and adding a lot of overhead to a simple addition operation. We also get this weird effect where we get a negative 0 when we flip the flag on a positive 0, giving us this negative 0. It feels mathematically ugly and intuitively quite nasty. Another option is to use 1's complement. In 1's complement, we flip each bit in number. A nice property of 1's complement is that when you flip each bit, this flipped inverted number complements the original, and when you add them all, you get all 1's as a result. If you think about the original number as a positive number, then we can think about this flipped inverted number as its negative sibling. If we do this for each bit, this is the number line. This is what the number line looks like for negative 4 to 4. You can see that on the left hand side, if we still think about this leftmost bit as a flag, then the inversion maintains that flag for negative numbers. Another promising property of the number line is that we are indeed counting up, even through the negative numbers. So from negative 4 to negative 3 is an increment of 1 and so on. But we still end up with this negative 0 property, which just feels wrong, and as we'll see later, will actually cause some arithmetic problems. Let's try some additions using 1's complement negative numbers to see how it compares to the flag system we were using before and how close we can get to additions being true and accurate. Here we do 2 plus negative 2. Again, we're doing addition just as we would in decimal. From right to left, we do 0 plus 1 is 1, 1 plus 0 is also 1, 0 plus 1 is 1, and the flag column 0 plus 1 gives us the 1 negative flag, And just to discuss before, this is the reason that it is called ones complement, because in every addition column we get the number 1. But if we look 1, 1, 1, 1 up on the number line, we see that this gives us negative 0. The answer, of course, we were expecting for 2 plus minus 2 would have been actual 0. So negative 0 doesn't feel too far away, but it's not quite right. Same for 4 plus minus 4. Again, we get all 1s because this is 1's complement, and again we get negative 0. Negative 0 doesn't feel wrong, but it's not quite right. Let's try a couple more additions to see if we can begin to spot a pattern. What's happening here with these 1's complement additions, which feels almost right, but not quite. Here we'll do 4 plus minus 2. This gives us positive 1 as the result, when we were expecting positive 2. So again, close, but not quite right. How about 2 plus negative 1? Again, 0 plus 0 is 0, 1 plus 1, 0 carry the 1, 1 plus 1, 0 carry the 1 again, and 1 plus 1, 0 and ignore the carry, giving us this time positive 0, if there was such a thing, where we were expecting positive 1. So again, close but not quite. And one final one, if we do negative 2 plus negative 0, just to see what happens with this negative 0 here, we get 1 plus 1 is 0, carry the 1. 1 plus 1, 0, again carry the 1. 1 plus 1 plus 1 here is 1, carry the 1. And 1 plus 1 plus 1 gives us 1, ignore that final carry. Gives us negative 3. Here, of course, we were expecting negative 2 because negative 0 should have no effect if it behaved like actual 0. But it has decremented by 1, and therefore we are off by 1. So given all of these addition operations which we've just looked at, can we begin to spot a pattern? For 2 plus negative 2, we got negative 0 where we expected 0. So we were 1 off in this number line at least. For 4 plus minus 4, again, we expected 0. And we were just, again, 1 off on this number line. For 4 plus negative 2, we would have expected 2. But again, we were just this 1 off. And the same for the following two. We are off here by 1 each time. So could we just add 1 at the end of every 1's complement addition to give us the right answer? Well, not really, because positive to positive additions, for example, aren't impacted by the 1's complement problems we're having. And also, the negative 0 is still going to get in the way, and answers which land on it still are basically mathematically nonsense. So instead of adding 1 at the end of every addition, why don't we simply add 1 during the conversion? This is 2's complement. To get a 2's complement representation, we flip all of the bits in the number just as we did with 1's complement. But then to that result, we add a 1. And doing this adding of 1 after the flipping has the nice property of only affecting negative numbers. And it was the negative numbers that were causing problems in the addition. And when your solution targets the problem area and nowhere else, you know you're onto a good thing. And this is what the 2's complement timeline looks like. Now, eagerly you'll notice that the leftmost bit still acts as the positive negative sign, but we have no negative 0 here. The reason that we have no negative 0, if you think about it, is when we flip this positive 0, we get all 1's, 1, 1, 1, 1, but then adding 1 to it causes all of these numbers to roll back as the overflow is ignored, getting us back to 0, 0, 0, 0. Therefore, the 2's complement of all zeros is itself. So now we've gotten rid of this negative 0 problem, how do our additions look? Here we can do 4 plus negative 4. Going from right to left, 0 plus 0 is 0, and 0 plus 0 is 0. 1 plus 1 is 2, so that's 0, carry the 1. 1 plus 1 is 0, carry the 1, which we ignore, giving us 0. 4 plus negative 2 gives us 2. Negative 3 plus negative 1 gives us negative 4. So this is quite exciting, right? Because we can store negative and positive numbers and add them without needing to know which they are. It means we have to do no manipulation in order to add negative numbers. And this works because we've created this continuous number line where each number increments 1 from the previous. And having removed negative 0, we remove the final barrier of being able to convert a positive number to a negative number, treat them as equals, and add them without manipulation or problems. And this is so simple and easy to implement in hardware, as we'll see in a couple of weeks' time, that this is actually how CPUs perform subtraction. They convert a number that they want to subtract to its 2's complement representation and then add the two numbers together, giving the correct subtraction answer. So we get these two advantages. We get the flag in the leftmost bit telling us whether the number is positive or negative, and we're able to add numbers without needing to know if they're positive or negative. It just works. And this is exactly why computers since the 1960s have stored unsigned numbers using 2's complement representation. One consequence of using this leftmost bit as a flag for a positive or negative sign is that we've now changed the range represented by our byte of 8 bits. Rather than representing the numbers 0 to 255, we now represent the numbers negative 128 to positive 127. And the reason that the negative range is slightly larger by 1 than the positive range is because 0 uses the positive flag in the leftmost bit. Of course, not all numbers in computers need to be stored with a sign. For example, addresses to bytes in memory don't need a sign, and therefore we can use standard binary representation using all 8 bits in the byte without needing a flag. Another example is lengths of strings or arrays, which again don't need to be negative and therefore can be stored as unsigned rather than signed bit. These unsigned numbers are stored in the standard binary format without a flag, and the computer is fine storing these unsigned numbers without the flag in the leftmost bit alongside the signed 2's complement numbers, as long as the program knows which is which. And that's how we store negative numbers in memory, using 2's complement representation to represent both positive and negative numbers, being able to add them and subtract them without any manipulation. In a couple of weeks' time, we'll take a look at how we can implement adding and subtracting 2's complement numbers in hardware. This has been 54M, and I'll see you soon.